Did you say something? Good morning, everyone. We'd like to welcome you to our Beyond the Scope talk today. We have Jennifer McConnell, the product manager for Protochips. She's going to speak today on machine vision in situ TEM for studying energy materials in particular. Part of the reason we're hosting this is obviously the major advancements in need for battery development and improvement in battery research. We have quite a bit of this developing in the state of Ohio and at OSU. And in that vein, OSU and Protochips is setting up a MOU to where we will have some of their holders and their newest Axon software on site so that we can perform these experiments in CEMAS and really see what is possible in energy research. So with that, I want to invite anyone listening to this or that might have some battery energy research that might fit into this sector or experimental technique to please reach out, whether it be industrial or academic. And yeah, let's let Jennifer introduce these products to you. So.
Thank you so much. Yeah, thank you. I'm really excited to have the opportunity. And everything I talk about today, I know there's a big corrosion group, obviously, there at Ohio State as well. And anything I say today is relevant to them too. But my name is Jen McConnell. I'm the product manager for the in situ TEM systems here at Protochips. And we're going to talk more about studying energy materials using in situ TEM, but not just in situ TEM, but a really newly augmented version that has machine vision software incorporated in it. Let's see if I can get my slides to cooperate with me. All right, we'll do it that way. And so just a quick outline of what we'll talk about today. Well, I'll do a quick introduction. It sounds like everybody here will probably have some TEM or microscopy experience, but just to make sure, I'll get the entire audience on the same page on what is in situ TEM and why in situ TEM can be valuable to these types of research, and then show some examples of some published work that's been done with our systems in the areas of batteries. And I do have catalysts in here as well. And so you can kind of see the different things you may learn from this technique. And then naturally, everyone's like, wow, that's really cool. How does it work? So we'll talk about how it works and how you're able to do these in the TEM. We'll talk about some of the challenges that are associated with this type of technique, and how we've incorporated machine vision software so that it's now a really complete front to back solution, and not just a tool to get introduced stimuli in the TEM. It's a front to back solution that actually addresses a lot of the challenges that we're going to talk about. Then I think you'll have a pretty big picture of a good picture of what can be done, and hopefully it's inspiring to several of you in the audience. So let's go ahead and get started. Quick introduction about what is in situ transmission electron microscopy or in situ TEM. And it's simply just a means of introducing relevant stimuli or relevant conditions into the vacuum chamber of the TEM, essentially. And so the analogy I like to use is, let's say you're studying fish, right? And fish, how they swim, how they eat, and you need to understand this process. Let's ignore the fact that you don't normally put fish inside of a TEM, but if you needed to, you obviously can't put the liquid and the fish, the water, the ocean inside the TEM as is. So you have to manipulate the sample. And this is true for a lot of materials that are studied in TEM. They're outside their native environment. You have to manipulate them so they're compatible with the vacuum environment in the TEM itself. Drying the sample, you're embedding it in a resin, let's say, you're freezing the sample. But if you're trying to study fish movement, maybe how they swim, if you're trying to understand how they eat, what they eat, this doesn't quite look right? You're not going to glean everything. You may learn a little bit about fin shape, how many teeth they have, and hypothesize some details, but wouldn't it be nice if you could really use the power of the TEM to get to the resolutions that you need, but also see the material in its more native environment, because you're going to learn so much more detail about how it goes from point A to point B, from pristine to degraded. Once you know what not to do, it makes it a little easier to figure out, well, what are the next steps to do? And so why incorporate in situ TEM into your research regimen? You may have been able to glean a good bit of value from that, but TEM, most powerful imaging tool, right, on the planet, essentially. You're getting down to atomic scale resolutions, and behavior of material, it starts at the atomic level. It's like the ultimate root cause analysis. You're using a TEM to understand how the atoms and the nanoparticles and molecules interact with each other under certain conditions. And so if you want to change the big picture here that you see when you're doing your bulk scale tests, which are just aggregates of bazillions of nanoscale reactions at once, right? If you want to change the big picture, you're going to have to understand those interactions at the atomic and the nanoscale to be able to do so. And so incorporating in situ TEM gives you information you can't get anywhere else. You don't have to hypothesize so much. You can now directly see these pathways of this material in its native environment, and that's invaluable. It's a great complement, especially to a lot of in situ bulk scale techniques that you're potentially doing. So everything I'm going to talk about today, all the research I'm going to show you in the machine vision, everything is associated and was done with our system called Poseidon AX. Poseidon AX is a liquid cell, as we call it. You'll hear me call it a liquid cell frequently throughout, because you're creating essentially a little cell of liquid in the holder and putting it inside the TEM. We'll talk a little bit more about how the system works in just a bit, but I just wanted to introduce, as I say the word liquid cell, or I may say the words Poseidon, that's the product that was used for all of the research and everything we talk about after. And it's our Poseidon with electrochemistry. So it's got an electrochemistry capability as well. So we'll dive into that a little bit more in just a bit. Let's start with what can you learn in the realm of energy materials and those types of materials, and starting with batteries. No question, batteries are a huge hot topic. A lot of money is going towards battery research for safer, cheaper, cleaner, less taxation on the environment. And when batteries fail, they're in everything. It's a very costly problem when they fail. And so with in situ TEM, you can study things like the solid electrolyte interface layer. You can understand dendrite formation and growth that's occurring during these charge-discharge cycles, and other mechanisms that help you understand failure, which can then help you improve the robustness and reliability and lifetime of the battery, reduce the environmental taxation of the materials and such over time. And you can't get to that resolution or that type of information with any other technique. So let's look at some examples. This is kind of an oldie but a goodie. I love showing this because it's a great example of what something you can see. This is from Lila Mehdi. It is from back in 2015, but she published some of the first work with Poseidon, looking at charge and discharge cycles of lithium batteries, looking at the dendrite formation and trying to hypothesize, how can we improve the situation? And so what you're looking at here is in these videos, what you're seeing is a working electrode. This is a portion of a working electrode that's inside that Poseidon system, inside the TEM, and it's surrounded by a liquid electrolyte. Here's your electrolyte here. And in this first video, we're running a charge-discharge cycle, and you can see the voltage, the potential there. And as we sweep in the negative direction, you're going to see lithium dendrite formation on that working electrode. And then as we sweep back into the positive direction, you're going to see a partial redissolution of the lithium back into the electrolyte. And the problem is what didn't dissolve, right? This is dead lithium. And as you continue charge and discharge cycles, so here's a second one, same everything, we just zoomed out a little bit. You're going to see that deposition and that partial redissolution again, but of course you've got more dead lithium. And with each cycle, you get more and more. And that's what leads to short circuits. This is what leads to fires. This is what leads to the fading of the life of the battery, capacity fading. And so trying to understand, all right, if we change electrolytes, maybe can we help the redissolution process and prolong the battery life? And here you can actually watch it happen. Calcium batteries, also an area of a big area of research as an alternative battery material. And you're looking at a kind of a similar story here. We're looking at dendrite growth and trying to understand how we can better redissolve the metal during the charge discharge process. What they're doing here, though, is looking at it as a function of current density. And at lower current densities, what does dendrite growth look like? At higher, medium current densities and higher current densities, what does dendrite growth look like? And what they see is at lower current densities, you get these kind of I guess the technical term they used were globular or islands, or, these kind of bulky growths. As you go to higher current densities, you see what you see here. It's more classic dendritic growth, these branches with these thin connector pieces that are more likely to break off. And so they did a really methodical study in trying to understand, as you change different variables, particularly with current density, how did that affect the growth of the dendrites, and how does that affect the redissolution? And so they found with lower current densities, you're able to get more planar, even growth, which was better for redissolution. You'd have more complete redissolution. And as you went up in current density with these more classical dendritic growths, where you have these branches that can easily break off and cause dead calcium, is where you end up in the situation like what we were just talking about, where the battery life is receding with every time that happens. And so again, understanding current density and its function on dendrite growth and how that affects the battery life, you're able to actually visualize it. And in this last example here for batteries, they're looking at enriching the SEI layer. The understanding is, and bulk ex situ testing shows that if you enrich the SEI layer with fluorine, and here they're using a fluoroethylene carbonate, when you enrich it, they see that the battery life is extended. The battery seems to be more efficient. Why is that? They've got a couple of videos here that I have to say aren't my favorite. I'm going to speed them up too because they're a little bit slow, but they're doing a charge-discharge cycle here. And you see the dendrite growth, the lithium dendrite growth here. This is without the additive, the fluorine additive. And then down here, they do a cycle with the additive. Like I said, I think the videos are a little hard to see. You also have a gas bubble formation occurring right up here, which is quite common during electrochemistry experiments in the TEM. But you can see their curves here, but upon more inspection, they summarize it with this kind of a cartoon here to understand. And adding the fluorine into the SEI layer and creating a fluoride-rich SEI, what they noticed is that during the first charge-discharge cycle, here's with the additive and without the additive and with, you see dendrite growth that looks kind of similar on the first cycle here, and you see redissolution very similar. But once you get into the second cycle, the dendrite growth, the morphology of it looks quite different. You end up without the additive with the more classic trees or branches. And then with the additive, you get those kind of globular ones again, which we've already learned from the last paper that they tend to redissolve better and more efficiently. And that's what they're finding here too, is that these branch-like, without the fluorine additive, you do get pieces that break off and you have dead lithium floating around, whereas you get much better redissolution, much less dead lithium when you have these like rock-like formations that form. And so this with TEM, this was the only way you're able to actually see this occur and the pathway on why this seems to improve battery life. Looking at fuel cells, also lots of fuel cell catalysis research being done with Poseidon, with the hopes of also adding it in as an alternative to batteries and vehicles and such. And we just got to find catalysts to go in the fuel cells that are robust, that are cost effective. So there's lots of research going on now looking at these types of catalysts and trying to find those magical materials that will serve the purpose well. And so with in situ TEM, you can actually watch these catalyst particles and see the electrocatalytic aging process. You see the surface to volume ratio decrease as the particle increases, the pathways at which that happens, the conditions at which that happens. You stress test to learn the structural and chemical changes that lead to catalyst degradation over time. Again, you see it. Once you know what not to do, it helps you to investigate what might be good to do. And so this works really well for catalyst studies in addition to battery. And so some examples here. This first one is using these nanoparticles that have kind of a cubic structure. And what researchers notice is that once you actually incorporate them into a fuel cell and start operating it, they only retain maybe up to a third of their catalytic activity. And so why is that? And in situ TEM was a really nice way to kind of observe what's going on as it degrades. In this case, unlike the battery examples, all of those were using electrochemical processes to replicate, the charge and discharge cycles, of course. Here, they're actually using the electron beam to kind of replicate the stress that would be put on these particles in a fuel cell. And so you can see the particles here. Are we playing? Try that again. There we go. You've got the particles here, and several of them have defects. You've got terrace defects, you've got corner defects, and then they also outline one that doesn't have a defect. And as they use the beam to apply stress to watch the breakdown process, the etching process going on here, it becomes very obvious that these defects have a huge impact on how quickly these particles degrade. Whereas that one without the defect here maintains its, for the most part, its shape and probably some catalytic activity for a much longer time frame than those with the defects. And so they were able to see this and understand which defects cause the degradation, and hopefully we can synthesize without them in the future. The oxygen evolution reaction, that portion of the fuel cell catalyst chemistry, is also studied quite a bit. There's a lot that's not known about the dynamics and the pathways of those catalyst particles, obviously. And so here is an example where we're looking at these cobalt oxide particles, which tend, they're interesting because they're a low cost material. There's a lot, it's plentiful, but trying to understand the process it undergoes during cycling of a fuel cell is really important. And so in this particular study, they outlined in great detail the studies that they did to understand beam effects from the electron beam. And while I didn't mention it in any of the other examples I showed so far, every one of these publications, as you would imagine, refers to the testing that they've done to understand how the beam affects the sample, how the beam affects the electrochemistry that they're performing, because obviously you need to understand that variable. When these materials are being used in the real life, that electron beam isn't there. So that's usually question number one, is how do you know the beam's not affecting the electrochemistry or what you're seeing? And so she did quite extensive methodical studies and reported them, and noticed that in TEM mode, she actually was seeing an effect from the beam and the dose they were using on the electrochemistry here. Whereas in STEM mode, where it's a lot easier to control your dose and control the area that the dose is being exposed to, she did not see any effects from the beam. So she did her work in STEM mode. And again, trying to understand the morphological changes over time. They notice that there is a morphitization that occurs in these particles as they undergo cycling. And you can see that change in structure here. And you can see here's the cycling they did. I think they did chronopotentiometry in this experiment. And as time went on, and the potential was run and continued ongoing, you can see the changes in the structure over time. So B, C, and then you've got an overlay of the two here. And so there was some significant amorphization that occurred. And they noticed that it's not reversible. That was one other thing they found here. It's not reversible to get it back to a crystalline state. One other thing they noticed as well was when they analyzed the size of the particles at the end of the in situ experiment, while it was still in liquid, they've got certain results here. They analyzed the crystalline portions of the particles. When they took the holder out and disassembled the cell and put the same chip, the same sample back in to do further analysis at higher resolution, they actually noticed there was quite a difference in the distribution of the crystalline particles and the sizes. And so, drying the sample for postmortem analysis in this case was not ideal. And had they not done this experiment while in liquid, they might not have realized such a difference. And so again, really changing the state that the sample is in, even just drying it out, can really affect the results that you obtain and potentially the theories that you pose. And then finally, this is just an example of a commercial fuel cell catalyst called Tanaka TEC 10V50E. These are really small particles, 3 nanometer size platinum particles. And again, trying to understand the pathways of electrocatalytic activity degradation, essentially. And this usually comes as the particles enlarge, because now you are losing surface area of having tons of small particles. As you lose surface area, you're going to lose catalytic activity. And they're just trying to understand which pathways were taken as they undergo the aging, the electrocatalytic aging. And so they ran up to 500 CV cycles to really replicate the stress of a fuel cell, and then did measurements on the sizes of the particles and how they changed over time from 0 CVs up to 500 CVs. This was really interesting because in liquid, for those of you that have a lot of microscopy experience, you can probably imagine imaging in liquid, it's not an atomic resolution technique. And so that is just an expectation you should go ahead and put in your brain. You're probably not going to get atomic resolution in liquid, but to be able to analyze 3 nanometer particles and push the resolution down to 1 nanometer. We've got as much equipment and chips and variations as possible to try and help you minimize scatter from the liquids, that you can get the best resolution that you can without potentially damaging your sample from dose or creating radiolysis products and such like that. So really cool, interesting examples. And like I said, usually the next question is like, how do you do that? How do you get that into the TEM? So the way they did it is that using our Poseidon system, you are going to hermetically seal an e-chip sandwich, as we would call it, in a TEM holder and put it in the TEM itself. So you're using 2 chips or 2 MEMS devices that each have an electron transparent window for the beam to go through and for you to view your sample. And you are going to assemble these into the Poseidon holder, where you have a gasket down at the bottom. You can see you've got electrodes patterned in the holder here. Your first MEMS device goes in, your second one does, which also has electrodes patterned on it that I'll show you in just a moment. And then you just put the lid on. As you're doing the assembly, those 2 electron beam transparent windows automatically align with each other, so you don't have to spend a lot of time aligning or tweaking to get them to be right on top of each other. We've designed it so it self-aligns, which makes assembly so much more straightforward. And then the electrical pads on the chip align with those on the holder as well for driving current through your sample. So this hermetically seals your sample, and you can flow liquid through, and it's completely safe to put it in the TEM. Just to show you a little cross section of what it looks like as we start flowing liquid. So if you remove the top chip so you can see better, you've got 2 liquid ports that meet here, in and then out after it goes through your chips. And we have the 2 liquid ports that are kept separate all the way up until, just outside the chips right here. If you ever have any experiments where mixing initiates a reaction and you want to see that initiation, you're set up in the best way possible to try and do something like that here, where they'll mix right here, and then you'll be able to view it right here, as opposed to mixing outside the holder. Once your holder is assembled, next step is the obvious one. You put the holder inside of the TEM. We've worked very closely with both JUL and Thermo Fisher Scientific, and they've tested all of our systems. They agree that all our systems are safe from multiple different standpoints. And you can see on the back here, the connections for the 2 inlets, the 1 outlet for the liquid flow, and then you've got an electrical connection here, which is where you would hook up your potentiostat to do electrochemistry. And then using specific MEMS devices in the holder, you can then perform electrochemical experiments, which is what you saw as examples in everything I just showed. So this system's been on the market for well over 10 years at this point. And of course, when it first came out, the early adopters were very happy to do some benchmark experiments to understand, like, can you do quantitative electrochemistry in a little tiny TEM holder in a very thin liquid layer and not in a beaker, and have it be comparable, the results be comparable to bulk and be understandable and relevant. And Oak Ridge at Ray Unisec at Oak Ridge was one of the first to really kind of jump on this with the Poseidon system using the model ferrocyanide redox couple. And found that the fusion constants that were calculated using different electrochemical scan rates and flow rates, they're consistent with literature, consistent with CV values in literature. And so we felt that this was early on, that quantitative electrochemistry is absolutely possible, even in a vessel that looks quite different than what you would typically do it in. And so what we've done is our best to miniaturize the standard 3 beaker cell that you would do the 3 electrode cell that you would do electrochemistry on the benchtop. We've got the 3 electrodes here. So the working electrode sits right on top of that viewing area in that window, which is what you saw in pretty much all of the examples here. You could see a portion of that working electrode, which is where a lot of the dendritic growth was occurring. You've got a large counter electrode here. And then you've got a reference electrode pattern right back here, a little bit out of the way from the working in the counter, so that if any bubbles are generated during the experiment, they don't interfere with the reference electrode and the job that it's doing. And so this is then assembled in the holder as the top chip. And we put all the electrodes on the top chip so that you can do excellent work in STEM. It's optimized for EDS and collecting X-rays for EDS, so you can get nice fast maps. And if you're curious more about that, why it's critical to have the electrodes on the top chip to do those things, we're happy to talk to you, but I'm not going to dive into it here. But just know this is optimized to do STEM. You can control your dose much better in STEM and as well as EDS with pretty much any EDS configuration that you have. So what electrode options do we offer as far as materials? The working electrode in particular, we offer a glassy carbon working electrode, or you can do a platinum electrode, whichever makes the most sense for your experiment. I know carbon is the most popular that is sold. It's very commonly used in benchtop scale experiments. So you can see here just an example of what it looks like on the chip in this kind of an optical microscope. What's also really cool about the carbon electrode, though, for electron microscopy is that it's essentially invisible to the electron beam, relatively speaking, usually to your metallic samples that you're looking at. And so you have a really nice wide surface area so that you can see what's going on top of it, and not only limited to viewing what's on the edge, what's going on the edges. Like with platinum, you're a little more limited, right? Because it's not so transparent. You're looking at what's going on the edges. So if you're ever working with particles, especially platinum particles, the carbon is really nice because you can see right on top of the entire thing, and you won't interfere with EDS having a platinum electrode and platinum in your sample somewhere. So glassy carbon or platinum are your options for your working electrode. The counter electrode is always platinum. And then the reference electrode, actually you have the options to use the platinum. It's patterned as platinum on the chip. You can use the platinum as a pseudo reference electrode, which a lot of our customers have done in the past. But we've recently added the option to be able to use a more standard reference electrode, something like silver chloride, saturated calomel, mercury sulfate, whatever might make the most sense for your experiment. We've designed a means of doing it where you can incorporate your reference electrode. It sits outside the holder, but you purchase them off the shelf from somewhere. So if you need to replace the silver chloride with something else, you're not buying something specialized or custom to fit in here. It's off the shelf from standard companies that sell those. And then you can also use it in your bulk experiments as well. And then you're really like the comparison between the two becomes even more straightforward, right? The less variables and changes you have between bulk scale and nanoscale, the better. And so we're really excited about introducing this because this has been a request for a really long time, and it's super user-friendly to install and flexible to change. You don't have to disassemble anything. So that is how you do it. That's technically how you get the electrochemistry into the TEM with our system. And we've done our best to make it as user-friendly as possible, but also as relevant to bulk scale as possible. We really want you to feel like the results you get from this, that you can actually draw some theories from it and use it as a complement to your bulk scale. But nothing good comes for free. So there's always challenges associated with every scientific technique, considerations to be wary of and such. And you've got them in 2 places with liquid cell in general. It's not really just our product. If you're doing liquid cell in general, whether it's a graphene cell like that you do homemade with our product, or with any other way introducing liquid into the microscope. Challenges with data collection. So obviously when you're collecting data, you're in the TEM, the idea is to get quality images. You're looking for the best resolution, the best contrast, and there are so many variables that affect this, especially when you are in a liquid. You have electron beam interactions to consider, sample movement, it's floating, you're biasing, it's going to move, liquid thickness, understanding and recording all the imaging parameters as you change them, the stability of the sample under the beam. All of this affects your end goal of data collection. right? And so the biggest one I really want to make sure we touch on here is electron beam interactions, because in liquid, things are just different than if you're imaging in the TEM, in vacuum, or even in gas. Liquid is a different beast. When you introduce the beam to a liquid, there are so many different things that can occur. In particular, the production of radiolysis products as the beam interacts with the liquid. So you have to be very mindful of the electron dose that you're administering and making sure you really baseline this. Understand it before you really start doing experimentation with the liquid you're using, and how sensitive is your sample to the beam, how sensitive your sample to the beam in liquid as well. So there's just a lot of good things you can do with the beam. We did one of the examples I showed, you were using the beam as the stressor, as the stimuli for the experiment. But there's a lot of things that are undesired that the beam can bring, and you want to make sure you are understanding what they are and deconvoluting them from any chemistry you're trying to report, right? And the problem with the beam and understanding the dose, the electron dose and such, is that there's not really a practical method that exists to help microscopists really quantify the beam. Everybody does it slightly different. Everybody's got different aged microscopes and different equipment that's calibrated probably a little bit differently. And as you are running an experiment, your dose rate and the electron beam, the flux hitting your sample is changing as you change aperture, spot sizes and such. So that's something you have to keep track of. And then even if you know your dose rate accurately, within situ, your sample is bound to move. And how do you keep track if your sample moves out of view and then comes back into view? How much dose was administered to that portion already of the sample? How do you keep up with that? That's a really hard one. And it's particularly challenging for in situ where things just move. And then reporting the dose for reproducibility's sake, and for your own and for your colleagues as you publish, with no standard way to report it. It's the electron dose, the last GRC, 2 GRCs ago for liquid cell, talking about standardized reporting for dose was a huge topic and a huge pain point in the community because of how much it affects liquid cell experiments in particular. And then when you're outside the lab, there's challenges that are data management. Again, it's not specific to our system. This is going to be TEM and in situ TEM, where you then add more variables. But you get really large data sets out of the TEM nowadays, huge gigabytes, terabytes of data. Being able to, how do you manage that visualization of these large amounts of data? How are you able to then look at what you've collected and make sense of it? What's the best way to visualize it? How do you share it with collaborators when they're so large and there's so much of it? There's also the FAIR principles that's been popping up recently. In Europe, it's mandatory now when you apply for money, for grants and such, that you explain how the equipment you're trying to purchase abides by the FAIR principles, which is a set of principles that have been put out there to try and improve metadata transparency, improve reproducibility between experiments, FAIR standing for findable, accessible, interoperable, reusable. I've got a slide on it I'll show you in case you haven't heard of it yet. And then metadata and image alignment. How do you take, let's say, electrochemistry data that you're using and collecting on a potentiostat and align it with the images that you just took to be able to tell a story? Those videos I showed you earlier where you see the dendritic growth and you see the CV curves or the potential curves to the right of it, those took weeks to months, and with the help of some computer science people to align and create those types of videos. It's not easy. And so a majority of these challenges that I'm just now telling you about, we feel we've actually solved a lot of them with machine vision software and incorporating that into the in situ system and making this a more holistic solution for bulk scale to nanoscale analysis, but then also being productive and publishing quickly. So the setup looks kind of like this. Now that they're all incorporated together inside the lab, which we have on this left-hand side here, you've got your in situ systems, that communicate with our machine vision software platform called Axon. And Axon is also communicating with the TEM. And so now you have a nice closed loop communication between in situ, TEM, and you have got all the software talking to each other, which I'll show you how that helps your quality of life at the TEM itself. But at the TEM, the module is called synchronicity. You also have a module called dose that you'll have at the TEM. And then when you're done with your experimentation and you move outside the TEM and outside the lab and you're trying to analyze your data and process it, that's where the module studio comes into play to help you do that. And again, the purpose of integrating machine vision into the in situ solution to create this like front to back workflow was to help scale bulk to nano, first of all, making sure that that is relevant for you and you feel confident in the results that you're obtaining. Accelerate productivity. So this doesn't take you 5 years to get good at what you're doing and publish something important. And then fostering collaboration and discovery, helping you to share your work with your collaborators and not make that so painstaking, which is good for everybody, right? All high tides raise all boats or something. There's a phrase. It's good. It's very inspiring too, if I say it right. So let me show you the different modules and how they are used with in situ. So the first module, synchronicity, it's the foundational software for all of our in situ systems, and it's meant to be kind of a virtual assistant for you in the TEM lab. In the past, we've heard a lot from the community that in situ experiments take 2 people. We need somebody running the microscope and we need somebody paying attention to the in situ side of things and changing the parameters. And that was really difficult. And so no longer is this the case. We've got Synchronicity, which is a machine vision platform that talks to the TEM. It analyzes the images coming out and it tells the TEM how to move the stage, move the beam. If you got piezo controls, how to adjust those so that the sample stays centered, even if it's moving. And so you no longer have to focus on operation, but you can focus on the sample itself and the experiment going on. So this video here, it's sped up. I just want to help you, see how it's occurring live for you. And this is Kate. And what you're looking at here is we've got our Titans operating software here. We've got TIA. And over here, you've got the in situ AX software, the Axon software. And here she's using our fusion system. It's not liquid, but I've got some examples for you in just a moment. I'm going to play. She's doing a heating experiment, and you're going to see the sample on TIA. It starts to kind of migrate up and to the right and then come back to the middle and then migrate and come back to the middle. And that jerking movement is actually synchronicity saying, hold on, Titan, the sample is moving. I need you to adjust the beam to recenter it, please. And it's doing all of that in the background. And Kate, you can see her hands are to herself. She's not doing any of the operation of the microscope. And so it's physically recentering the sample for you. And then it also performs a digital correction at the same time so that what Kate can do is pay attention to the Axon screen, the sample itself while it's undergoing heating, and, just make sure she understands what's going on. Does she need to change parameters? Does she have what she needs? Can she leave? And so she really can focus on the in situ portion. It also has a focus assist to help with focus. You can calibrate it and tell it what you think good focus is and what not. And it's also taking notes for you. All the parameters from the in situ system, from the camera, from the TEM, everything is being embedded in all the metadata, and it's going to index it for you so you can filter on it and you can find it really easily later. And so ultimately what we want to do here is lower the learning curve for in situ, especially if you're not a frequent TEM user. Adding in situ on, it can be very daunting because again, there's a lot going on. And so let's lower the learning curve. Let's lower the barrier to entry. Let's make it more accessible and less scary to some people. Your focus on the sample increases. You'll reduce your experimental iterations this way as well. And you generate higher quality data the first time because everything's stabilized already. You don't have to post-process and then come back 2 weeks later because you realized this really doesn't look that good. And so here you see an example of this one's in gas. It's a copper nanoparticle in an oxidative environment. It's undergoing the Kirkendall effect. And this is what she would see on her screen right here. And it looks nice and steady and still. We created this video right out of Synchronicity, but you can see what's plotted here is movement. You've got Z, X, Y. I know the numbers are a bit hard to see, but you're moving like hundreds of nanometers total in all three directions. But everything is nice and stabilized. So again, virtual assistant that's controlling the microscope for you that can see and observe much better than the human eye can. So an example in liquid, no matter what your sample is doing, here we've got let me pause it for a second just to explain. Here we've got some gold particles in a gold chloride solution, and we're going to use the beam to initiate dendritic growth of gold on these seed particles. And then we start heating to exacerbate the growth. So you see the growth starts here, and then you can see the temperature ramp kicks in, and we start heating. And despite all the chaotic dendritic growth and such, everything is stabilized and still. And again, that's what you see as the microscopist at the TEM, and you don't have to do anything to achieve that. And it's all happening live, but whether it's floating, something's precipitating, dissolving, undergoing electrical bias, reduction by the beam, or being heated, it can control movement for everything that might happen in an in situ experiment. For those that might not have a lot of experience with in situ and you're not quite sure how much movement we're really talking about, this is a little bit of an extreme example. And this is also not our system. This is a Gatan 652 bulk heating holder. So it does work with other systems as well. So a lot more power than like one of our holders, which is MEMS based. There's a lot more power going to the sample than what you would with a MEMS holder. So on the left side, you see the heating ramp. You've got quite a bit of movement, and you can imagine if you're sitting at the TEM, you have to figure out the knobs, the focus, and everything to try and recenter that and hold that still to try and get some high resolution imaging while you're heating. It's just impossible at that point. But that's where your virtual assistant comes in. Synchronicity is like, I got this. And this is literally what you would see as the microscopist. So it just, your brain waves open up so much when you don't have to focus on the instrumentation, and you can really just figure out what's going on with your experiment in the sample. So that's Synchronicity. For dose, the module dose is also what you're using in your TEM lab. And again, I cannot emphasize enough, particularly with liquid cell, how important it is to understand your dose and report it accurately. But even outside of liquid cell, the electron beam is not any of the materials you study in the TEM, they likely usually operate somewhere without an electron beam. It's got some effect, whether you feel it or think it or not. And so understanding it and reporting it, it's going to just become more and more important anyway as time goes on. And so the dose module comes with a really special Faraday cup holder that we've designed. You've got a Faraday cup area for measuring beam current, and then you've got a transparent area for measuring beam area. So that way, if you are imaging and there's beam exposure to an area that you may not be looking at, like in TEM mode, the beam spread might be outside the field of view, but your sample's still getting exposed. Even if you're not looking at it, it's tracking that. It'll understand the beam area, and it's tracking that for you. And so you get to build a nice calibration dose profile for your computer, or excuse me, for your TEM that's stored in the software. And then as you work, as you change spot sizes, apertures, and stuff, the software is automatically going to calculate the dose for you, and it's going to use that drift correction to track where on the sample it is. So even if your sample goes out of view and comes back in, it's going to remember. And so you can use these dose overlays to make colorful maps to kind of indicate where the dose has been exposed already in your sample. Yellow is a lower dose amount, and then as it gets closer and closer to purple, you're getting higher dosages there. You've got spot fading tools to understand when crystallinity changes occur using FFTs. But here you also have the ability to jump around on the stage to areas that have not been exposed yet. So this video shows the use of what we call a dose atlas. So we've turned on a dose map, and you're going to see a low magnification box pop up right here in just a moment. You see this is in STEM mode. And that's a low magnification view of the stage. You can see where we are because it was colored with the dose maps. And she double clicked and moved over to the left. It's now been exposed with dose, so it's colorized, and she double clicked and moved back over to her original position where the dose was already being calculated. So it's running through it again here if you want to watch it again. You got STEM mode because you got the square dose maps. But as you double click and move, like she does right here, it blanks the beam so that once you get over to that space on the stage, then you're not exposing the entire pathway to that point with the beam. And it'll keep track, like I said, you can go back, you can see exactly where you've been. Once you've kind of been around the stage a lot, you're going to have lots of pink, yellow, purple dots all around that dose atlas to see where you've been. So it's keeping track of that for you. And then finally, the last module is called Studio. And Studio, you're primarily using outside of the lab for data processing, but you can actually pull it up in the lab and review everything you've captured for the day in that moment and figure out, am I done? Am I not? Has this been like changing so slowly? I haven't been able to see it. This helps quite a bit in the lab as well, but Studio looks like this. You've got an area for the images, you get the metadata panel and the analysis panel where you got FFTs in here, and you'll have measuring tools, and all the parameters that are collected are listed here. And you've got a timeline showing where your images are over time. You can plot things like temperature, current, voltage, and try to look for trends as one parameter relative to another. And it just really helps to visualize large data sets, and you can visualize multiple at a time. This is a file repository, so you can pull up sessions like that just over and over again from 3 weeks ago, 2 weeks ago, 4 months ago, years ago, and just be able to visualize. You've got everything about the experiment there. All of those dose parameters I was just telling you about, dose rate, maximum dose, it does some statistical analysis, median, mins, and such. That's all recorded as well, and you can visualize them again via dose maps in Axon Studio as well, and export to video with the dose maps on them, so they're really cool. And everything is drip corrected too, don't forget. But for the electrochemistry in particular, when you're doing energy materials research and you're doing these electrochemical experiments, we're the first system that's actually incorporating all the electrochemistry metadata, aligning it with every image for you. And there is no question which CV was done and has which images associated with it. And you can filter and find, CVs 10 through 200 and export those to video, but all your metadata is collected, and it becomes as easy as this to just look through everything. You just kind of rewind, fast forward, just like you would a video. Oh God, back in the old days when you had a VHS. You can turn your dose maps on and off, but here we're plotting current and voltage, and these are multiple CV cycles. So you're seeing like that sweep from negative to positive. That's what you're seeing down here. And it just makes it so easy to kind of swipe through and just view everything and find the important areas of your experiment. And then you can export. So you can actually plot the CV cycles just like this right next to the images in Studio, and then export to video just like this in seconds. Everybody used to take weeks to months, and now you can plot it and export it in seconds. It's absolutely insane. And it's so awesome that my video is freezing, but you get the point. And then for sharing with collaborators and such, again, the data sets are large, but this allows you to find, so you can plot, find something that's important. Here we found something along the lines of where this peak is, and we just want to send this to our professor. So we can create a little album for our professor right here, and then we can do something called pack and share, and it will zip up just that little portion, just that little album, and you can much more easily send that to somebody else than sending the entire data set and trying to describe where you want them to look. And the best part is this Studio software is free for everybody. So you can send data sets to anyone, and they can download Studio and open it up and see it just like this. They can analyze it, they can plot whatever they want, they can export their own videos, and you can average and bin and stuff like that when you're doing videos. And so it gives a lot of autonomy, and you don't have a lot of questions coming back and forth about what were the parameters here, and what was the dose rate when you did this? Can you see any trends associated with dose rate? Well, now you can plot dose rate along with the images and kind of look for trends that way too. So the visualization aspect is so much easier than before, where you're using maybe a few different softwares and you're trying to manually align parameters. I'm just going to touch quickly on the FAIR principle. Some of you may have heard of it, some not, but it is growing in the US in particular, where if you are applying for grants, you may get questioned on how the equipment you're buying is going to support the FAIR principles and abide by these guidelines of making metadata reporting, metadata access findable, accessible, interoperable, and reusable. And having these machine vision in situ systems, you're already there. The Axon portion of them does all of this for you with all the records it keeps, the alignment it does, and the fact that you can export it into an Axon database file. You could technically upload that to the publication website as supplementary information if you wanted, just like a small album or portion of it, and then anybody can download Studio. It doesn't get more transparent than that, but that might be a bit too transparent. So yeah, we meet each of those principles fully with this type of software. So I just want to touch again and kind of recap, the challenges we talked about earlier, where we felt like if we had a smart software, machine vision based software that we incorporated with our in situ systems, we can touch and solve a lot of the issues that you see here. Electron beam interactions with dose, sample movement with synchronicity, imaging parameters are all recorded with synchronicity, sample stability usually is a function of dose and how stable it is under the beam. So you've got a nice quantitative way to understand that for reproducibility's sake. When you look at data management, everything here under data management is covered with a holistic software solution that when incorporated with in situ, you now have a front to back. There's also a load of sample prep tools that we have that really get you from sample prep to publication, but I didn't cover that here. Happy to talk about it though, if anybody is interested in what those are. And then I just had a moment of looking ahead where we really feel like expanding capabilities in the in situ space, very important always. And that's something we're looking to do with the chips, with the hardware, so that we can meet more market needs, especially as projects evolve. So we're absolutely looking into that. But don't be surprised to see more software modules as well that help solve pain points where you can't solve them with just hardware. And so why not just have a holistic solution of both? And so this is some of the most advanced in situ equipment on the market. It's not just a tool for applying stimuli. It's really supposed to be a solution for a research project. So we're trying to touch all the bases for that. We do have a gas cell as well called Atmosphere that is also based on the Axon software platform. And then our Fusion AX, which is a heating and electrical system, also based on the machine vision platform of Axon. And I'm happy to go through any of those with anybody that's interested, or take any questions if there are any.
Thank you very much, Jennifer. That was a wonderful overview of your hardware and software and
Thank you.
how that can apply. Do we have any questions in the audience here? No. Let me see, are there any online? I have a couple that I'll ask.
Yeah, sure.
From the electron transparent windows that you have on your MEMS chips, what are they made of?
Silicon nitride. They're a low stress silicon nitride. Mm-hmm.
Do you have an average thickness that you expect them to be?
Yeah, they're usually about 50 nanometers thick each.
Okay.
It's the fine line we try to walk between robustness and resolution.
Sure.
Usually though, the bigger knob to turn for resolution is not so much window thickness, but rather liquid layer thickness.
Mm-hmm.
And so, yeah, we're trying to, yeah.
You mentioned that, but so do you have the ability to change the thickness of the layer based off of the hermetically sealed chip?
So we've got a few different ways you can do that. We've got a huge catalog of spacers for our liquid cell chips, so that you can, based on the size of your sample, you can get it as thin as possible for the size of your sample. We also offer different window widths, because as you make the window narrower, you're going to prevent any of that window bulging that occurs from the pressure differential of the vacuum of the microscope and the pressure inside the holder. So we've got a couple of knobs there that you can turn to try and increase resolution. And then there's workflows for trying to remove liquid from the holder itself, or from the cell area, to do some high resolution imaging and then reintroduce liquid. Some people want to do that and have been successful with it, but there are caveats to it as well. And so, but it's possible for sure. So there's a few different knobs you can turn.
Okay. Awesome.
Is the Axion software dose calibration, is that strictly predictive, or can it also control the dose being used in each study?
Did you hear that?
I think so. Were you asking if the dosed hardware / software actually controls the beam, or does it just measure? Is that correct?
Yes, that was the question. Yes.
Okay. So right now it will only blank the beam when it's moving, when you've double clicked and had it moved like a gross amount of movement. Let's say at the moment it's not controlling the beam. We did not know how much control people wanted to give up and have the software do for them at this point. And so right now you are calculating current and you're calculating beam area, and for different settings. So you can change from STEM to TEM when you do this, change spot sizes, apertures, whatever conditions you might be moving through during your experiment. You do a calibration for each. It's like a few minutes for each set of conditions, and create that calibration curve. And then it is reporting to you what the dose is. It allows you to set levels. If you've done some baselining and realize at this dose rate or at this cumulative dose, I don't want to get anywhere near this, you can set these levels in the software, and then that's the color gradients are based on the levels that you set. So as it starts to turn yellow, maybe you're getting close to a level that you've set to warn yourself to watch out. As you get close to red, those are levels that you've set in there. So it is telling you and warning you that it's getting closer, but it's not adjusting the beam or changing the beam. At this point, it's just helping you understand what your dose is without you having to really think or do math or anything like that.
Mhm.
Okay.
Is that something that would be interesting, you think? Like, would you want it to control the beam in some way?
So on some of the, on a cold fix system or on a monochromated system, right? One of the things that make them very powerful is the ability to fine tune your dose to what you need, right?
Mhm.
So on conventional TEMs, you're limited by your apertures and whatever your source is. But with these newer systems, we actually can tune it to within a pico amp of what we want typically, right? So yeah, that would be a huge benefit in my opinion, that the system could take control of that, and then you could define it to maintain a current dose or current condition on your sample.
No,
Another thing that happens in those systems is sometimes the current fluctuates over long experiments. I don't think we'd probably be doing an experiment long enough that
yeah,
that it would, but that's something that you could maintain as a constant dose.
that's great feedback. Thank you. It's not the first time I've heard it either, so I'll be sure to feedback that this is coming from multiple people. So thank you.
Sure. You good, Austin? Yeah, okay. We have a couple online now. There's a person in Taiwan that you may be familiar with. They've been using the Poseidon for up to 2 years now. But quite often they get a question is how accurate is the temperature readout on the MEMS device? I mean, I know I guess we can go to high detail on this, but have you profiled your chip? I mean, are people using secondary methods? Yeah, what kind of temperature distribution and variation in temperature readout would you expect?
Yeah, so if you're doing heating, which we didn't really talk too much about today, but if you're doing heating with the heating chip in liquid, we do characterize all of our heating chips, whether they're for fusion, for the gas cell, or for Poseidon. We characterize them all. We've got an infrared camera here where we understand resistance versus temperature for all of our chips. For Poseidon in particular, we spec the accuracy to be at 95% or better. And so we feel that if you set a temperature for the chip, and for a liquid, it goes up to 100 degrees Celsius. But if you set a temperature, that you'll be within 95% or better of that temperature. And the way it's heating, the coil is embedded in the chip and it's heating the entire cell of liquid. And so that's what we're referencing, that we feel that the liquid is within 95% of what you are requesting, and it's heated uniformly throughout the entire the liquid in the holder tip.
Okay. And then one more. It's from a person that worked with a Poseidon a few years ago, but or the Axon software. They're asking, is the Axon Studio available for personal computers, or do you still require a high-end PC, probably with a GPU involved?
So Axon Studio, the offline processing software, that is for use on personal computers and laptops, and that's free. Anybody can download. If you go to success.protochips.com, you can download it, and there's a sample data set up there as well for you to play with. So Studio does not require using synchronicity at the TEM, which is the only place you would really use it. The
And that will come with the, right, if you have Axon, that would come with this, you have a computer that you deliver with that.
Yes. So that's the only one that really requires it. Otherwise, Studio for processing data is for right now. I use it on Parallels on my Mac, and we're definitely working towards a Mac solution though as well. So those with Mac can use it on their personal, but absolutely take it on. We want you to put it on your laptop and take it with you for sure.
So just to clarify that point, the slides that you were showing at the end where you were going through your data and doing the post processing, you can run that in Parallels on a Mac?
Yes.
Excellent. Excellent. Okay. Any other questions from anyone? All right. Well, Jennifer, I really appreciate your time. We're very much looking forward to getting this in and seeing what we can do with it. So thank you very much for your time and this partnership.
Yeah, we're really excited. Thank you for that. But reach out if you've got any other questions, if anybody after anything.
Most definitely. Okay. Have a great day and enjoy your weekend. Enjoy the holiday, everyone. Bye-bye.
Thank you. Bye.